Hello, I'm Dr. James Dborin, co-founder and head of research at DoubleWord AI, and today we're continuing the Behind the Stack series of videos where we talk about advanced tips and tricks when building self-hosted systems. And in this video, we're going to be talking about tricks you can do in self-hosted systems to speed up the inference of agents in particular. So we're obviously going to be talking about agents, so let's define what we mean by an agentic workflow. We're going to have a user, we're going to have an LLM, and we're going to have some set of tools that the LLM has access to. And the way this works is the user is going to send a request to an LLM. The LLM is going to, maybe it's going to think for a bit, maybe not. It's going to know it has access to some set of tools. The tools communicate to the LLM and they can communicate to each other, for example, through like an MCP compliant interface. So the user sends a request. This might be something like, what's the weather today? The language model thinks, it says, I probably need access to a weather API. So it sends something to the tools. It sends a message to the tools asking for access to the weather API. The tool has made it known to the language model. The MCP server has made it known to the language model that it has access to a weather API. So the tools return back the API call. The language model thinks again now with its new response from the API. It might make other calls along the way, and eventually it sends the final response back to the user, which includes all the information from the tool calls. And so this is broadly what it looks like, and the way it looks like, or what the language model really sees, is a series of messages along the way. So it first gets a message from the user with your request. Then it appends to that the model's thinking. I mean, usually this is called like a system or something, but then the model thinks for a bit, and then you append to this the tool response, and this continues for a while until you get the model's final response to the user. And then this is the end of the series of chat messages. And so let's model like how you would cost this if you were using an API-based system or a sort of naively constructed self-hosted system. So what happens is first your user just sends the request to the model and you get charged. So we're going to define that, we're going to split the total cost into like the prefill tokens or the input tokens and then the output tokens. This is usually how API providers charge for access to their API. So initially, you get charged for the user's response, and then the model's thinking. So that thinking might include like the API call to a tool response or something like that. Then, when you get that response back from the tool, you need to resend that to the model for it to process again. And so now your input is the user's input plus whatever thinking came out of the model plus the tool response. So we're going to call this, we're going to keep it, we can keep it like that. And then the output is another thinking step, but I'm going to put this thinking step in green because this might be calling another tool. This might be saying, okay, I'm ready to give my answer to the user, things like that. So this is now thinking in green. So let's say it calls another tool. I'm going to get the response back from my tool server, and now I'm going to send it back to the model to do something else with it. Like this might be the time to respond. So now the total tokens that in your input are user plus thinking plus response plus this thinking set of tokens, the one in green, plus like a green response. And now there's going to be maybe another thinking step. You could have very large tool uses, very many tool invocations, and this is going to go on and on. And so all in all, like you're seeing this quadratic increase in cost because this user prompt is reprocessed every single time, as is this thinking response is now reprocessed and you're recharged for it in every single following request, as well as the request getting longer and longer and requiring new tokens. And so this cost can rapidly spiral out of control. Now, you might be thinking that you could use, for example, the OpenAI caching set of tools, or the Anthropic caching set of tools. Most providers now have some sort of ability to cache. But unfortunately, this ability to cache isn't quite flexible enough as of today. Sure, you can send this response in to cache it, and then all future responses won't have to cache the user response, but it won't cache, for example, the thinking tokens. And so first you cache, maybe what you instead do is first you cache this user response and you don't pay for the user tokens, and then on the second one you cache the user and the thinking and the response, and then you don't have to pay for these tokens. But if you want to get this all the way, you're going to be paying this quadratic cost in the caching process. Like, you're still pre-filling with these tokens, so you're still being charged for these caching tokens. And so ultimately you're still paying this quadratic cost, quadratic in the number of thinking steps that the model has. And you're paying this cost both in time and in money. So because you have to wait, this is increasing your time to first token. Like, reprocessing these long prompts takes time. It's not a short process, and you're being charged for it. So it's like quadratic in both ways, and that's obviously bad. And the API caching mechanisms aren't flexible enough to actually make use of the caching APIs to make this cheaper. But if you choose to self-host models, you actually do have a sort of flexible enough mechanism to make this quadratic cost go away. So most inference engines nowadays come with the ability to do prefix caching. What happens in prefix caching is, if I have a long series of inputs like we have here. In fact, I'm going to copy this over. If we have like a long series of responses, what I have flexibility to do in a open source inference engine, for example, inference engines that have this, I mean, pretty much all of them nowadays. VLLM has this, SGLang has this. Pretty much anything you want will have this, or will have this now implemented to some level of maturity. And the usefulness of this is that what I can do is, on my GPU, I have my KV cache, and I've talked about the KV cache in a bunch of other videos, so go and watch those if you're not sure what this is. But in short, it's like a block of memory stored on the GPU, and this is like the model's memory. This is the model's working memory. This is how it knows what was said in previous, like earlier on in the response, and it uses this for the processing of its current token. And when I process the first user message, it's going to sit in some set of blocks, and then I'm going to process the thinking messages and the response messages, and then I'm going to process the sort of second set of thinking messages, and they each are going to get their own set of blocks in this KV cache. And the nice thing is that in the API models, in an inference engine without prefix caching, when you resend in this the next response, so you go from user to user plus thinking plus response, you throw away the fact that you already had those sets of words in the KV cache. You get rid of them, you erase them from the model's memory, you make it available for overwriting, and this means you have to reprocess it, and then in the open source models you get the quadratic cost again. But if you are using the prefix caching engine that these inference engines provide, what you can do is, between these responses, you can ensure that this user set of tokens stays in the KV cache and in fact is reused, so that now when you do the thinking response, you just reuse that block of memory, and you use these blocks together to have the model output its response. And then when the green tokens come in, the next thinking and the next response, these three are already in the KV cache, so you don't reprocess them, you don't have to pay that cost again. And then you use them for the green responses, and then this is going to continue for the orange tokens, and so on and so forth. And the outcome of this is that for really long agent chains, where it makes lots of tool invocations, you get much faster time to first tokens, because you're not repaying these responses. So time to first token, maybe by which maybe I mean the first token of the final response, because typically you have to repay the processing costs for all of your intermediate steps. But in this way, once an intermediate step is processed, it never has to be reprocessed. And each new response is about as expensive as the first one. Whereas in an API call, each new response is more expensive than the last one. It includes the processing time of all the previous responses plus the new one. But in an open source setting with prefix caching, it just requires the processing cost of the new tokens, which is obviously much cheaper. And there isn't really much downside to this. These prefix caching engines are now really efficient. There's almost zero overhead. There's almost zero overhead from this process. So if you have multiple workloads, and one doesn't benefit from the prefix caching, maybe it's like a RAG system where the documents tend to be unique or the chunks tend to be unique, then that can mix with the prefix caching workloads, and there's almost no overhead. And in distributed systems like Dynamo, it goes actually a step further. If I have two LLMs, maybe two copies of the same LLM on different hardware, and a request comes in, you can have a load balancer that looks at the request and identifies that this LLM here at the top actually shares a prefix with this request, and hence, because prefix caching is turned on, this request is going to get sent to this language model and not to this one. And requests that don't have a shared prefix, like your RAG request maybe, end up in this LLM here, and your agent requests, which often share prefixes with previous invocations, always end up here. And you get this sort of natural partitioning of your models into high prefix overlap questions and low prefix overlap questions, or into distinct groups that share prefix caching, all because of this load balancer, which keeps in it a picture of the KV cache and knows roughly which language models have high overlap. So in this video, we've spoken about prefix caching as a unique benefit of self-hosting language models. And if you're suffering with slow or expensive agent invocations and you're using API-based systems, or you're using unoptimized self-hosted systems, it might be worth switching to an optimized self-hosted environment, and you might find yourself getting much better costs or much better speeds by using the particular structure of agent workflows and designing your infrastructure around that.